To thank the organizers for arranging the symposium, and the speakers for providing a stimulating series of talks. Specifically, of course, thank David, Adam, and Rolf for arranging the whole thing. I wasn't going to say much more, and I'm not going to talk about cryptophagids. But since I never seem to throw anything away, I recently found a lecture that I gave the Coleoptera Society in Montreal about 15 years ago. The title was The Systematics of Coleoptera, a Millennium View. I also had it subtitled Recollections of an Old Fart. So although much of that talk involved higher classification of beetles, what I thought it appropriate at the time to comment briefly on the technological base and intellectual environment available to me and my fellow students at Berkeley in the late 1950s, early 1960s, and compare it with the situation in the year 2000. I think this is even more relevant today, given the staggering technological advances that have occurred even in the past 15 years. So we'll get a time machine here. Whoops.
You have to go up, John. You have to go up on this.
Oh, go ahead. Here. Go back to Berkeley in late 1950s, early 1960s to a room crammed with graduate students in what was then known as Agriculture Hall at UC Berkeley. Now, although Xerox produced the 914 photocopier in 1959, copying machines were not generally available. Storage and retrieval still depended on the typewriter and the card catalog. I once had several ring binders full of typed original descriptions and translations and loads of 3x5 index cards. Computers existed. The first IBM computer was produced in '53 and Fortran programming in 1954. But they were certainly not generally available to, and personal computers were still in the realm of science fiction. I didn't start using a computer myself until I began my first job at Harvard in 1965, and then it was a matter of punching data into IBM cards and handing them over to computer technicians in another department. Oops, it's not the one I want. Next, previous. I think they got confused. No matter.
Must have got confused.
Yes. Handing them over to computer technicians in another department and waiting for the printouts from the big computer no one ever saw. Now, scanning electron microscopes began to be available, at least in the UK, in the mid-1960s, but were virtually non-existent at this time. And photomicrography was beset with all kinds of in-depth focus problems, especially for the minute insects which some of us were working on. Certainly this was the age of the pencil, the pen, the manual typewriter, and the slide rule. Now, evolutionary biology at the time was still basking in the light of the Renaissance that took place in the early 20th century with the works of Ernst Mayr, George Simpson, Theodosius Dobzhansky, G. Ledyard Stebbins, Sewell Wright, and a number of others. However, the new systematics, as Julian Huxley termed it, was still a bit bogged down when it came to classification and its relationship to evolutionary history. Classifications were meant to be consistent with ideas on evolutionary relationships, but the nature of these relationships were not really clear and were decided on the basis of phonetic similarity combined with intuitively derived evolutionary scenarios. The evolutionary school of Ernst Mayr was dominant, and the latest textbook on systematic zoology was published in 1953 by Meyer, Lindsley, and Usinger, my future boss and two of my mentors at Berkeley. In 1950, a German dicterist named Willy Hennig wrote a book called Phylogenetic Systematics, that even Germans found difficult reading, or so I was told. But the English translation had not yet been published, and the eventual ramifications of this word could not even be guessed at the time. Terms like clade and cladogenesis were used by some authors, but cladistics in the modern sense had not yet even appeared in the literature. In 1963, Sokol and Sneath began to shake up the taxonomic community with their book called Numerical Taxonomy, and their claims that current systematic work lacked objectivity and repeatability, which was probably true. In fact, Stebbins was so angered by this that he challenged them to a debate, which they did have at Berkeley shortly after that. Wagner had formulated a dendrogram generating algorithm, but these were merely the rumblings of distant guns. It was not till 1969 that Klug and Ferris developed computer software for the production of Wagner parsimony trees. In the field of historical biogeography, the Sherman-Williams paint theory, well, looks like we've got them all messed up. Let's try it again. Okay. The Sherman-Williams paint theory of biogeography, which I needed to have this because most of you wouldn't know what I meant. What it was all about, everything was thought to have evolved in the northern landmass and filtered down to the southern hemisphere. Darlington advocated this in his book on zoogeography in 1957, influenced by various vertebrate zoologists of that time. Although some workers supported Wegener's 1912 theory of continental drift, plate tectonics theory was as yet unknown. In the U.S., at least, adherents of ancient supercontinents were considered to be part of the lunatic fringe, along with a South American botanist named Croizat. Terms like Pangaea, Gondwana, and Laurasia were unknown to most entomologists, let alone the general public. In the field of insect evolution, the paranodal theory of wing origin from lateral turtle lobes remained unchallenged in courses being taught at universities. Although the details of wing origin are probably still disputed today, it is now generally accepted that the wings evolved from articulated appendages. Now, the term molecular biology was unheard of, although preliminary ideas on the subject were taught at Berkeley in a course entitled Physico-Chemical Biology by Daniel Mazier, which I didn't do very well in. Watson and Crick first published on the structure of DNA molecule in 1953, but it would be some time before the impact of that discovery penetrated the entire field of biology. My own favorite order, Coleoptera, Crowson had recently published his major work on the classification of beetles in 1955 with an update in 1960. And although this represented a giant step in our thinking about beetle evolution, it was still several years before this became generally accepted. In Montreal, I went on to talk about major advances in technology and ideas that had occurred between then and the year 2000. On the technological side, not only were there quick copiers, digital cameras, scanning electron microscopes generally available, but personal computers were becoming more powerful than mainframes in past years. I also mentioned phylogenetic programs like N86, Hawk, Maclay, Winclata, as well as a variety of advances in computer graphics. And finally, I mentioned the increasing use of DNA sequence data for phylogenetic analysis, something which at the time was just beginning to take off. It would take days to cover the important technological changes that have taken place in the field of insect systematics since that lecture was given. Digital cameras have continued to improve. Image stacking software is generally available, producing far better images, excuse me, and advanced computer graphics. And here's an example of light micrography with automontage software versus scanning electron micrographs, showing the different features that can be seen using the two methods. But in addition, you had people like Ralph Beutel and his associates in Germany using traditional section combined with advanced computer graphics to produce images of internal anatomy, such as this head of a beetle about 1.5 millimeters long, and also X-ray tomography for the study and illustration of musculature without sectioning, as shown in this section of the thorax of an Arctostomaton beetle. Molecular biology, of course, has made unbelievable strides. Phylogenies based on single genes and a limited number of taxa are being replaced by those based on numerous genes and thousands of species, such as that of Hunt et al. 2007, or Duane McKenna's recently submitted work based on the Tree of Life project. And there have been concomitant changes in methodology for sequence aligning and phylogenetic analysis. But I'm in no position to pursue this topic any further, since my aging brain tends to bog down when confronted with terms like Bayesian analysis, blastoline, genomics, transcriptomics, and numerous other things, which I find a bit over my head. However, I am very happy to see them and very happy to use their results. I think I can sum up by saying how fortunate I've been to see all these changes taking place, and I hope that as a fledgling octogenarian, I can continue monitoring the progress in our fascinating field. Thank you.